Hi everyone! I am Saniya, and this little cutie is cute little Yankee. And in this video, we are going to learn about how we can do multiple test correction in R. So if you have a set of p-values from whatever experiment that you're doing, a set of probability values from any experiments, coming from testing multiple hypotheses again and again and again repeatedly, and you need to adjust for those p-values. How do you do that? I have other videos talking about the concepts involved in various statistical correction techniques like Bonferroni correction, for instance. But here I'm going to show you how you can do this in R for a variety of methods. So the idea of multiple test correction is, well, an analogy is just like Yankee trying his hand at the slot machine in the Krusty Krab right behind me. So Mr. Krabs has this slot machine with all these little teddy bears, like, you know, this cute little British teddy bear Yankee. Aww. He likes it. But this other little red coat as well. So there are a lot of different teddies in Mr. Krabs' machines. And the key idea is that with multiple test correction, what you're correcting for is the fact that you are repeatedly trying your hand multiple times on the slot machine to win a teddy bear. You know, just like in the back, there are lots of teddy bears there. But the idea is that you're repeatedly trying. So it may not just be one time, one hypothesis test, but it can be many hypothesis tests that you are doing. It's like many times, and each hypothesis test is just like trying your hand at the slot machine. So you may come up with one teddy or multiple teddies, or maybe you could have no teddies at all, no teddies. But whether you have one teddy that you've got in Yankee or two teddies, the idea is that you may have tried out on the slot machine so many times. So we need to correct for that, because it's not just like Yankee's a skilled pro that won these two teddies at the slot machine. It's not like that. It's not like he's skilled. It's just that he may have gotten lucky by having maybe 20 tries or 30 tries and he just got two. So we need to correct for that. And that's what we're doing. We may have a set of p-values, and each p-value comes from one experiment, but we fundamentally have to adjust our p-values to consider the fact that we have done multiple hypothesis testing. So if Yankee says, am I a good slot machine player? I'll have to say, well, I'll have to adjust. I'll have to adjust. You may have gotten two teddy bears, but after how many tries? How can we weigh that? So that's the idea. That's kind of like an intuition for multiple testing correction. But I do talk about this more in other videos. So right now, we're going to see how we can do this test correction in R. So we're going to try our hand at the slot machine, win the teddies, but see how we can correct for them. Oh, I think he wants a teddy. Let me put it here. Aww. He's so cute. He's just like my teddy. You know, got him the slot machine. He's very, very cute. So yes, let's get started. And the example from today I'll be showing is if I were to look at 30 genes and the gene expression levels between patients who have severe COVID-19, so they end up in the intensive care unit, and patients who do not have severe COVID, they are not in the intensive care unit. So it's a real example, but I want to just show you, like it's a toy example, but from a real data set for COVID severity. And I want to show how I can do multiple test correction using a variety of methods. And some of these methods I do talk about extensively in other videos. The key package or the tool that we'll be using, it comes right in the base package in R. But before we dive in, Yang saying, please ensure that you like, subscribe, and share this video as well. And please do reach out with any and all questions that you have. Okay, so let's get started. So this will be the tool that we will use. It's called p.adjust. Adjust p-values for multiple comparisons. And it is available in the stats package. So you probably don't have to worry too much about downloading this. He kind of wants the other teddy too. Feeling, Yankee's feeling just like a winner. He's just like his own little teddy. He's so cute. He's excited as well. So he won in Mr. Krabs' slot machine, these two little guys. But we won't, I probably won't ask him how many times he tried till he won these two. But anyways, the key idea is that Squidward tries so many times, he goes bankrupt just trying to win even one teddy. But SpongeBob has a way that he keeps winning multiple teddies, and Squidward just can't handle the fact that SpongeBob can get those teddies and he can't. He's like, what is the secret? He wants to find it out, but in the process, he keeps trying again and again and again. So ultimately, he gets one teddy bear, but the cost is that he sold his house, he's given up his salary, just gives up everything just to try to win one teddy. You know, a quarter at a time, it pays for itself indeed, because he keeps on losing. He keeps trying till he gets that one hit. And that's what we're trying to adjust for, that there are multiple tries, multiple tests that we've done. And if we typically have the key p-value threshold at 0.05, the alpha, that's the alpha. If we reject the null, if the p-value is less than 0.05, then we need to be careful now and make sure that we reject the null only when necessary. So here, this is the tool that we will be using. We'll be using p.adjust, adjust p-values for multiple comparisons. So given a set of p-values, it returns p-values adjusted using one of several methods. So it's called p.adjust. You just input your p-values in here, and you can try a variety of these methods: Holm, Hochberg, Hommel, Bonferroni, BH, BY, FDR, and Null. So FDR and BH, they are exactly the same. So they're just based on people who know them by different terminologies. These are exactly the same. And we'll go through that. But the key idea is that we just need to put in a numeric vector of p-values. They can have NAs inside them. And I will be adding some NAs to our vector just to show you. If it's anything else, you have to make sure it's as.numeric. It has to be a numeric, a vector. So if you have some p-values, they could be characters, for instance. We just need to make it as.numeric. And this has to be a correction method, one of these types of methods. And n is the number of comparisons. The default is just to take the length, so the number of p-values you have, use that for your test corrections. So if we've done like 10 genes or 10 p-values, for instance, then this would by default be 10. If we have 30, like in our situation, then this by default would be 30. So the number of p-values, those are the number of tries that you have. So the number of tries that you have. So Yangshi, how many times did you try to win in the slot machine, huh? Ah, he's trying so many times. He's trying to put his paw up. Like I just tried 5 times. No, he tried many times to win. Yes, you did. Yeah, he's not making eye contact. Oh, he's very cute. He's saying rock on. Okay. Look, he's even avoiding eye contact. Oh, he doesn't want to face how much time he spent winning these 2 guys. Okay, so now we're going to get started with the example here. So in this example, what I want you to see is this is an example of doing multiple test correction. So I run differential gene expression analysis results between a group of 6 COVID patients who are in the ICU, intensive care unit, severe COVID, and 6 patients who are not in the ICU, don't have severe COVID. So I ran this in the script here. I ran it in the script here. I ran those results and analysis, and I have this result here from this. So it gives its own adjusted p-value. I ran this using a package in R, but let's ignore this right here. It gives them a p-adjusted value. But the key result is that it gives you a base mean, a log 2 fold change, the standard error for this fold change. So there's a mean. So it's comparing the non-ICU patients with the ICU patients. So non-ICU, I said, is not severe, and the ICU intensive care unit is severe. So these are 30 genes here, like ABHD5, ACBD6, BMI1, CCR2, all of these UROS. And I'll talk about these more in another video, but these are the walled test p-values that we get from this kind of comparison. These are the p-values here in this set of results. So what I'm going to do is I'm going to just turn it into a data frame. So I just do data.frame here. So it is now a data frame. So it is 30 observations of 6 variables here. And again, we're going to ignore this p-adjusted value. It has its own default that it returns, but we're going to focus on our p-values here that we get, the raw p-values, not the adjusted. We're going to find our own way for the adjusted p-values. But you can see all these genes here, the means, and what the key criteria we're focusing on in this video is on this p-value right here. That's what we're focusing on, this p-value. So what I'm going to do is I'm going to just do p-values. I'm going to just extract this p-value column from here. That's what this does, just takes the p-value column from this data frame. So this is my set of p-values right here. So it can be all of these p-values right here. These are the corresponding p-values. So again, e to the negative 0.05 just means like there may be multiple zeros in front. So it's 4.344 times 10 to the negative 5, which is quite a lot of significance because it's pretty small. Whereas this one is 7.57 times 10 to the negative 1, which is just 0.757. So that is pretty high. So it's definitely not significantly different between both groups of COVID severe, the ICU patients, and COVID non-severe. So that's what our test was trying to do. So basically, that's what our test is trying to do. We're trying to determine which genes are statistically significantly different between the COVID severe patients in the ICU and the COVID non-severe patients, the patients who are not in the ICU. That's what our test is trying to do, and we have those p-values from there. But the fact is that I was testing 30 genes to come up with this. 30 genes, 30 different hypothesis tests, 30 different p-values. So I need to kind of do some sort of selection for that, because originally what I would have is I would have had like so many genes, for instance, being significant. Like all I have to do to find the significant ones is I have these p-values here. And I can just do like p-values. And this will tell me the p-values that are less than 0.05. How many do I have? I can take the length. And this will tell me that I have 11 p-values that are less than 0.05. So those are significant genes according to my criteria here. That's what I would say. I have 11 that are statistically significant based on this 0.05 threshold here. Another way is to visualize which genes those are. So if I have a data frame, you can select the rows where the p-value is less than 0.05. So this will give me the same set of, I'm looking at the p-values again, not the adjusted. Let me just get rid of this here. Because we're going to find the adjusted, but there are many types of adjusted p-values. So we can see that these are the 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. These are the 11 genes whose p-value is less than 0.05 that are considered statistically significantly different. That's what's key here, is that we have these 11 based on this p-value being less than 0.05. That's the criteria that we're looking for. So they are considered as significant based on this, but we need to adjust. So all of these have p-values less than 0.05. So we think that they are statistically significantly different between the severe and non-severe COVID group. So we need to adjust for this, basically. So what we're going to do is we have this set of p-values here. And I'm going to kind of get rid of this for now. We'll come back to this. So the goal is that this was where I had shown you guys this documentation for the p.adjust function. So it's called p.adjust. You have p, which is your numeric vector of p-values. They can have NAs in them. You have a method, like a correction method, like Holm, Hochberg, Hommel, Bonferroni, BH, BY, FDR, and none. And we have the number of test comparisons where n should be greater than or equal to the number of p-values. Like in this situation, I can just see length of p-values, and it would be 30, because these are the 30 p-values that we have. Because again, this is the dimensions of the results that I got from the COVID-19 severity, differential gene expression analysis. I had 30 rows by 6 columns. So I had this as my results. We will find our own adjusted p-value. We're going to use this p-value. You can stick with their raw p-values, but I'm giving you an example. Like, let's just say you have your own p-values, or you want to calculate this using your own correction method. Then how would you do that? So Yangshi would probably say, he would probably choose a correction method that's not so strict, because he wants to see make a winner, because after all, he won this over here. Yes, he did. He won this very much. he won this. He won this very much. Because Yangshi, after all, Yangshi won this with some great difficulty. Aww. Aww. So he's gonna probably want to choose his correction method that makes him look like a winner. It's okay. I already think you're a winner. He wants to choose his own correction method. So basically, now what I'm gonna do is I'm gonna use these p-values here that we have, and I'm just gonna try out different methods. So all I'm gonna do here is I'm gonna show you what happens if we change each of these methods right here. We're gonna focus on adjusting this right here. We're gonna see what happens if we try Holm, Hochberg, Hommel, Bonferroni, BH, which is the same as FDR, BY, or none. That's what we're gonna do here. So the adjustment methods include the Bonferroni correction, in which the p-values are multiplied by the number of comparisons. They also have less conservative corrections, are also included by Holm, Hochberg, Hommel, Benjamini and Hochberg, which is called BH, or FDR, which stands for false discovery rate, and Benjamini and Yekutieli, 2001, which is called BY. We can also have none, and none would just do no adjustment. It's just going to be the original p-values. But we're going to see each of these now. So now the first thing we're going to do is we're going to look at Bonferroni correction. So Bonferroni correction. Now let us look at the Bonferroni correction. So in the Bonferroni correction, what we're going to do is we are just going to take our p-values here, as always, and this n will just be the length of p-values. This is the default, length of p-values right here. We don't even need this because this is the default. But I'm just going to show you with this being specified just so that you can remember. So all I have to do is just change the method to Bonferroni. That's all you're going to see, that I'm just changing what I'm calling the method. So for Bonferroni, I just call this method Bonferroni right here. Yeah, that's all where I make the change. The p-values are multiplied by the number of comparisons. So we're going to see that these are the Bonferroni corrections. And if I put these side by side, oh, eeks. If I put these side by side right now, this is p-values, and then this is the Bonferroni adjustment. We can see that each of these and these right here, we can see what this is. In fact, what you'll notice is if I take this, each of these values, and if I multiply it by 30, if you remember, we have 30 genes here, 1 to 30, 30 multiple tests that we're doing. 30 is the number of tests that we're doing. So if I just multiply all of these, each of these values here by 30, the number of tests, I will get this respective value, not times 30. This times 30. This times 30. So all we're doing is it's just multiplying the p-values by the number of comparisons. That's all that it's doing. So for instance, let me show you even the head of this. This is the first few rows. This one's a very nice method. So this is the head, and we can just see that if we multiply this guy right here by 30, we'll get this value right here. So it's just being multiplied by the number of comparisons that we have, which is just 30. And then the result. It's just the same. This 1.3 times 10 to the negative 3 is what this is here. That's all that Bonferroni is doing. Another example is if I were to take, let me just take the third one right here. And if it's over 1, it just rounds it to 1. Because sometimes they can go over 1. So it just chops it at 1, which is the highest probability you can have. That's the rule. So this would be, this is what we did here. We just multiplied this 2.24 times 30 again, and we have this 6.74 times 10 to the negative 5. That's what it's doing here. And you can see that in this situation, this is just like 0.61895, so it's 61%. If we multiply this by 30, it's going to be over 1. It's going to be 18.56855, so it's going to be so high. So they just chop it at 1. This is 1 times 10 to the 0, which is just 1. So this is just how we can do the Bonferroni correction. We just plug in Bonferroni here, and then I can just do the length. Which I'm finding which Bonferroni p-values is less than 0.05. So now instead of 11, we have 5. This is 5. We find 5 are the p-values that are less than 0.05 out of the 30. So instead of 11, we have 5. Whereas before, when we were doing this, we had 11. Now instead, for the original p-values less than 0.05, we had 11. Now we just have 5 using the Bonferroni correction. So that's how you do Bonferroni correction. We will look now at the Holm correction. The Holm correction, which is in 1979 by Dr. Holm. So for the Holm correction, all I'm going to do is just change this method from Bonferroni to Holm. That's all I will do. So I'm going to have these p-values here. These are the p-adjusted values, adjusted p-values. That's what ABJ means, adjusted p-values. So I can compare before versus after. So I can see that this is the p-values before, and this is after the Holm adjustment. So you can see that this is 4.344 times 10 to the negative 5. And now it goes to 1.17 times 10 to the negative 3. So by and large, whenever we do adjustments for p-values, those would tend to be higher p-values, because a higher p-values would mean like, where this is to the negative 5, 5 zeros in front of this. Now they're just 3 zeros in front of the number. So 2 decimal places, 0.00117, instead of having, 4 decimal places and then this starting. So these adjusted p-values would be higher, because what they're trying to do is they're trying to raise the p-value so that we won't have as many significant findings. So they're trying to raise the p-values so we won't have as many significant findings. Yes, Yanchi? So by raising the p-value, we won't have as many significant results instead, because we want to reduce the number of false positives, of number of genes that we are thinking are statistically significant, number of whatever it is, if it's genes or it's something else, whatever it is, the number of p-values that are detected as being statistically significant, we're trying to adjust for that. So we are trying to make some adjustment, and the adjustment would usually be to increase the p-values so that not as many are significant, because even though Yangshi won these 2 little guys here, maybe we want to kind of adjust for it. We want to kind of see, okay, how many tries did Yangshi get to win these 2? Did he just win them all on the first go? Is he very skilled? Or did he need so many? Did you need so many? He's quiet. So that's the adjustment. So the p-values for the adjusted method should typically be higher. So we can see that these are the p-values for the Holm, then with that Holm adjustment. And I can similarly also find the number of p-values that are statistically significant based on the Holm approach. I'm just going to put in that here. So now instead there are 6 p-values instead of 11 from before. There were 11 before, and now there's just 6. But in Bonferroni, there were 5. So this is kind of different. And now this is the next kind of test correction, the Hochberg 1988 correction. So it's not to be confused with the Benjamini-Hochberg procedure. It's just a Hochberg correction in 1988. So in fact, this is a little bit of history behind this next method of Bonferroni procedure. In fact, this is a little bit of history behind this procedure for the Hochberg in 1988. So it was published in Biometrica here, and it's called a Schreiber-Bonferroni procedure for multiple tests of significance, and it's by Josef Hochberg. So they say it's a simple procedure for multiple tests of significance. You know, that's what our p-values are. Each of them is a test. And in our case, each of our p-values in our case is a different gene that we're testing. Is this gene differentially expressed between the severe COVID patients and the non-severe patients? It is a test. So that's what it is kind of doing. It's a test. So what they're saying here is that it is, it's a simple procedures for multiple tests of significance where we have the individual p-values. So it's sharper than Holm's 1979 sequentially rejective procedure. Both procedures contrast the ordered p-values with the same set of critical values. Holm's procedure rejects a hypothesis only if its p-value and each of the smaller p-values are less than their corresponding critical values. This new procedure rejects all hypotheses with smaller or equal p-values to that of any one found less than its critical value. So these are just kind of showing different correction methods that are tried. So when we say Hochberg 1988, we mean this approach here. And later on, Josef Hochberg would come up with the next principle, but we'll get back to that there. But he would partner with Yoav Benjamini. But we're looking at the 1988 correction. So all we have to do is to try Hochberg. So just written by him. So we just do p-adjusted Hochberg. I'm just using p-adjust again. And you'll notice that the key differences so far is that instead, I'm just changing this method to be Hochberg. Instead, before it was Holm, and before that it was Bonferroni. So now I'm just going to call this Hochberg here. And we can see this here. We can see the p-values before for the original data, these 30 p-values, 30 different tests. And this is the Hochberg 1988. This is what we get after using the Hochberg correction. That's what our adjusted p-value would be. And I can similarly find how many of these Hochberg p-values would be less than 0.05. So let me just plug this in here. So that's what which is doing is it's just finding the location of the indices. Remember, this gives us the values, the p-values for the adjusted. It takes in our set of p-values from here, and then it just does this adjustment for them. And when I'm doing the C-bind, I'm doing a column bind where I'm going to have my p-values in the left. That's what this first thing will be. And the second will be p-adjusted Hochberg, so I can compare them. That's what C-bind is, a column bind. And now I'm just going to be looking here and finding which of these is less than 0.05. So those will be considered as being significant under the alpha of 5%. So that would be 1, 3, 6, 15, 18, 25. So this one would be significant. It's less than 0.05. This one is 0.983, so it would not be significant. You can see how it kind of went from here to here. It's really not significant. It went from 0.61895 to 0.980. So the third one is still significant here. 6.52 times 10 to the negative 5. So it's still significant. It was very significant before, and it's still very significant now. It's just that at decimal place, it's just almost like 10 times bigger here. So basically, I'll now take the length of this. I'm going to find that this was 6. So similarly, there are 6 of these that are less than 5% after the Hochberg. So instead of 11, there are 6 significant genes in our situation, 6 significant p-values. And then I can always find those p-values here. I can always do Hochberg. I can put in these indices. And these are the corresponding p-values. I can always go back to the original data set that we had. And I can always put in these specific rows. Remember, it's data frame, rows, comma, columns. So I can always just put in these specific indices, which will give me those specific rows. So I just put this in here. And I'm going to get the 6 ones from before. We can ignore this, and these are the p-values that we're going to see that from before that are still significant under the Hochberg correction. These are the corresponding ones. These are not the p-values we will use. We will use the Hochberg p-values to find the significance, but these are in the original data set. These were the genes. ABHD5, ADPRH, CCR3, KBTBD6, OAS1, STXBP5. That's what it looks like. I just put this in here. So in our data frame, I just put this as a criteria to filter the rows. So now we finished this. So Yangshi, what happened, Yangshi, is that Hochberg basically came up in 1995. He partnered with Yoav Benjamini. So Yosef Hochberg partnered with Yoav Benjamini in 1995 to find a less conservative and more appropriate testing correction measure. And together they call it the Benjamini-Hochberg procedure for test correction, named after both of their last names. The Yangshi is different from the Hochberg test procedure in 1988. So 7 years later, there's this new method which uses the same Hochberg person, Yosef Hochberg. It uses him, but also Yoav Benjamini. And they call this the false discovery rate. So it's a method of conceptualizing the rate of type 1 errors in null hypothesis testing when conducting multiple comparisons. So they use this idea of false discovery rate. So I'll talk about this more in other videos, but I just want you to know that this FDR is just the same thing as the Benjamini-Hochberg procedure. So that's what I hope you can take from there. It's the same thing here, and it's another correction procedure. So that's what I hope you can take from there. So next we will be looking at this, the Benjamini-Hochberg test correction, and then we'll go back to the Hommel 1988 correction. But I just wanted you to see that the Benjamini and Hochberg 1995 correction, also called false discovery rate, there are 2 methods that you can use, and they're both the same. It's just that the people use different things. So we can either use FDR or BH. That's the key thing here. If we use the BH, then it would look like this. If we use the FDR, it would be the same exact thing. They're just giving you the option to use both. In fact, if we put both side to side, you will see that they are exactly the same. Both of these are exactly the same. All of these are the same either way. So whether you use p-adjusted BH or the p-adjusted FDR, they're both equal. So these are exactly the same between the two. So we can either use method BH or method equals FDR here. Either will work for this. They are exactly the same. And then I can also just look at the original. I can just choose one, like Benjamini-Hochberg is the same thing as a false discovery rate here. So I'm just going to put one of them there, and you can see kind of how this Benjamini-Hochberg procedure, also called the FDR, how these are different, you know? How, again, each of these p-values will be kind of less than or equal to these p-values here. That's always going to be the case. So the p-values will always be less than or equal to the Bonferroni, Hochberg, Holm, Benjamini-Hochberg, Benjamini and Yekutieli. All of those will be kind of less than or equal to those. But I just want you to see that, you know, whatever these are less than or equal. These p-values are less than or equal to these adjusted p-values. So I just want you to see this, that p-values will always be less than or equal to adjusted p-value. Adjusted p-value raises it up so that it may no longer be as significant before. Because the higher the p-value, it's going to be less likely you'll reject the null. And the key goal is to reject the null hypothesis and to come up with a discovery, hopefully. So the p-value should be less than or equal to the adjusted p-value, no matter which correction method we are using. This will tend to be higher, if not the same as the original p-values. That's a key thing, guys. Again, the key thing, Yankee, is that the p-values will be less than or equal to the adjusted p-value. No matter what approach we're using, that should be the case. Because we want a stricter approach to filtering out significant genes. We want less significant genes or less significant p-values to be gone, and we want to have a fewer number of significant p-values that we're having. We want only the very, very, very highly likely p-values to remain, because if you keep on, trying so many times, to get hits, we need to adjust for it, right? Like if somebody gets these 2 teddies after just trying 5 times, then you've tried like 50 times, then they must be better, right? We need to kind of penalize you a little bit, Yankee. For trying so many times together, you must have given a lot of effort for it, right? But you may not be as good as a person who has got it in 5 tries. So even the cat, oh Yankee, it does not mean I love you any less. Aww, he feels kind of guilty. But that's what this test correction is doing here. That's from the Benjamini-Hochberg. I just wanted to also show you that we can, again, count the number of significant genes or number of p-values under the BH procedure. So there would be seven significant p-values under this BH procedure. And just again to remind you that the p-values are the same whether we use FDR or BH, it will just be the same here. You'll get 7 again here too. They're the same. Both of these are the same. This is the same as this. FDR is just using FDR and BH was using BH, but it's the same thing. Benjamini and Hochberg is known as the false discovery rate. So I know I skipped over Hommel 1988 correction. That's that same year Hommel came out with the test correction method. So we just have to put in Hommel instead. I was just trying to show how Hochberg in 1988, the correction kind of evolved when Benjamini kind of came in. These are the last names. And then they made the BH procedure. But there's also Hommel. So Hommel here is another approach in 1988, and the method is just Hommel. So we can just see what these p-values look like if we try Hommel, and we can kind of compare these p-values versus the Hommel adjusted p-values here. And what we can also do again is we can just find out how many significant p-values we have, which correspond to the number of significant genes in our situation, but your situations may differ. So here, this would be 6. Currently, BH is having the most p-value significant after the filtering. So again, this is giving you significant number of significant results. This is 6 for Hommel. So I told you how Hochberg, kind of developed a method. First, Hochberg saw this method in 1979 by Holm and said, hey, I can do better. Let me come up with the Hochberg 1988 correction. But then 7 years later, Hochberg had partnered by then and put out another paper with Benjamini about the BH procedure, the false discovery rate, the Benjamini-Hochberg procedure 7 years later. But Benjamini also did something similar. Benjamini, just 6 years later, came out with another method with Yekutieli in 2001, so right after the millennium and the Y2K scare. Came out with this procedure called Benjamini and Yekutieli correction. It's called the BY correction. So all we have to do is just put BY. So the same Benjamini from here, partnered with Yekutieli. And this is the BY correction. And as a probability, again, all of these have to be between 0 and 1. So you can see the p-values and then the adjusted p-value using Benjamin and Yekutieli. So we can again see how many p-values are significant after this correction. And this will be 6. So there are more testing correction methods out there. I just want to show you the ones that are supported by this package and some of the key ones. There's also story Severity approach. There are many different approaches out there. Aww. And he's going to try to find one that makes him look more like a winner. Woohoo! But I also want to show you that there's this none method here that allows you to even just put in none, and it returns the original p-values. No correction. You just put in none here. You just put in none, and it just kind of returns to you the same. These are exactly the same. They're equal. That's the p-values and p-adjusted none. It's just the same p-values as before. And just to also help cement that as well, we just put in this none, we should get 11 as before, 11. 11 indeed, they're the same. So if we want to just compare these side by side, how all these multiple testing correction methods, how they all fare, if we had to compare them side by side, the ones that we've discussed, for this set of 30 genes, for this set of 30 tries, how do all of these kind of compare? So again, just like a quick recap, what we found is we tested out a few different methods. We looked at Bonferroni correction, which was the strictest, and just said 5 significant genes, 5 significant p-values. Holm just said 6 significant p-values. If we want to find, again, those significant, those 5 significant ones, all we have to do is we can just put this in as the row, and I can get this in here. For Bonferroni versus strictest, it just identified 5 p-values, in our case, 5 genes that are different for 1, 2, 3, 4, and 5. And again, we're not looking at their default p-values from DEC, which is another package I used to get these. But basically, these are just the 5 that we get from Bonferroni. Now we just plug them in here, and we can see those 5 significant genes that we were, and those 5 significant p-values that we were talking about. Then we looked at Holm. Holm was 6 p-values that are significant, and these are the row numbers for them. Because remember, in this data set, we have row numbers that we can access, and that gives us those specific row numbers for Holm. For Hochberg, we had 6. For Hommel, we had 6. For Benjamini and Hochberg, we had 7 significant p-values, which was the most. For Benjamin and Yekutieli, we had 6 significant p-values. And for none, for the original, with no adjustment, we just had 11. So now if we just look at the all comparisons data frame here, I can just do a data.frame. I can have each of these vectors, so each of these, the none, the Holm, Hochberg, BH, which is the same thing as FDI. I just want to hit that home. You get it home. FDI, Benjamin and Yekutieli, Bonferroni. So I'm going to have it like this. Oh, and also what we can see is that this is an example of a gene whose expression level. I've normalized the data. We are comparing between the ICU, which is in red, and severe, and non-severe, which is blue. Non-severe is blue, and severe ICU is red. So that just shows this is one of the genes that we were looking at, because you can see that GLE1 is one of these. GLE1, we have its p-value for GLE1. And other metrics from this data frame that we can pull up. It's just a continuation of the same. I just wanted to show that to you. But now we've seen all of these, and I'm just going to stitch them together into this data frame. So this is the all comparisons data frame. So for all 30 of these p-values, all corresponding to each of the 30 genes that we were looking at. And again, to see those 30 genes, which were being tested in our situation, the ones that were being tested, row.names of this data frame will give us those genes. Remember, each of these here is a gene. So I just do row.names, and these are the 30 genes right here. These are the 30. And so all comparisons, the data frame. I can let me even add in the gene name here. Let me even add in a column called gene names and set it to be equal to this row names here. This row names is just those 30. And I can just see this here. Now I have the gene name as well. So I can just view this. Oh, 1 second. So now what we can see here is these are the original p-values. Let me see that. These are the original p-values. This is, again, if there's no adjustment, they're exactly the same. This is the original p-values, which is also just the same as if we do the adjustment. You see the 30 entries. So the original p-values here. None is just no adjustment, which is exactly the same. If we look at none. At Holm procedure. So we basically just took this raw set of data and we were kind of running it through everything. None is just no correction. Holm, Hochberg. These are just the same. with each other. Benjamin-Hochberg and FD are just the same with each other, and Bonferroni. So we looked at quite a few different ones. And we can see how the p-values tend to relate. That's why we got less significant ones, because we were looking at how many p-values are less than 0.05. Well, what happens is these p-values tend to be increased for the adjustment, so that we will have less false discoveries being made, less genes, less p-values that are considered significant than are actually the case. It's kind of weighing them by the number of tests we're doing. All of these p-values will tend to be higher than these p-values here. And we can see the corresponding genes. So these are the p-values that we get for the comparison. You know, if we're trying for this GLE1 here, for instance, comparing severe versus non-severe, getting the p-value from the walled test. And then similarly, you know, for our p-values, in our case, they correspond to genes and differential gene expression analysis. In your case, they could correspond to other things. But we're having a p-value and we're just trying to adjust for it here. And you can see the results from each of these test corrections. And you can see the results from each of these test corrections here. So the key idea is just to change the method that you're calling in this p-adjust function. Just change it, try out, you know, and for this method, just try out different methods. And if you don't remember, you can just call this function right here. You can just call p.adjust.methods and it will name out all of them for you. This is in the default stats package. You don't need to install anything, but you can just call p.adjust.methods and it will name out all 8 options. And but again, BH is just the same thing as FDR. They're the same. And none is really no adjustment. So what I also want to show you is they talk about one thing, which is that you can use NA values here. If you have NAs, it just won't consider, it's not going to throw any error here. So I just want to go back and just show you really quickly that we can have NA values here. But before I do that, I just want you to again remember that this p-values was the length of p-values, 30. And now I'm going to just append a few p-values. I'm going to be appending NA 1, 2, 3, 4, 5, 6. So 6 p-values. So now if I call length of p-values again, now I'm going to expect a higher number, like 36. So if I see this p-values right here. So there is this NA here, not applicable. And it needs to be numeric. Like this would work here. It would now, even with this NA, it would just like ignore it. And it's just going to have p-adjusted Bonferroni. So if we have these p-values here, let me even look at p-value 1. And let me look at the Bonferroni. So to show you, this is the p-value and this is Bonferroni. And length of p-values is 36. So if I take my original and I multiply it by the number of like now p-values, right? I just added a bunch of p-values here, random things, just to show you that we can have NA values as well. So if I just multiply this by 36, then I'm going to get 0.0015693663978. So even if there's an NA, like I still count it. So if you try to do this and multiply it by 35, saying, oh, 35 are non-null, you would not get the result that they got here. So this is the Bonferroni value, which is matched exactly by this, by multiplying all the genes, all the all the p-values that we have, even if there is an A here, even if there's an A. Because if I take this original p-value of 4.344 times 10 to the negative 5, and if I multiply it by 36, which is the number of p-values, I get the result for Bonferroni correction. Now, if I multiply it by 35 and I say, hey, one value is NA not applicable, so there's really 35 p-values, that's not going to work, because I'm going to get instead the Bonferroni value of 0.00152, which is not what I get from this method. So this method, it's multiplied by the number of comparisons, including NAs. If you don't want NAs to be included, you have to just remove them from the p-value vector that you're using. Otherwise, they will be used in the calculations. So again, like in our p-values, we had these 36, including this NA, and we have to multiply it by 36, each p-value, to get the Bonferroni. But you can see that we can call all of these. We can call it even with this NA being there. It's just going to keep the NA there. It does not matter. But if I, for instance, like let's just say I did p-values and I tried to add in, like this means append to the, add this to element. 878, 0.500. Okay, I'm just adding these two to it. So now my p-values looks like numbers. So before it went from here to a bunch of numbers, which can't be good because it needs to be numeric. Like that is the requirement. So since the requirement is that it needs to be numeric, we just have to do as.numeric to make it numeric. So the reason is like if I just stuck with p-values as is, as character, like if I just did class of this, it would be character. I can do str structure and it will be a character vector. If I stuck with this and tried this Bonferroni, it would still work, but I don't really think that this is a good idea. It would still work, but I strongly do recommend that if they tell you to use as numeric, then just kind of go through the steps and have this as like p-values equals as dot numeric, and just to follow that along. So you just want to be careful because if they've documented it and they need certain requirements, some things may not be the best if you don't do that. So just kind of make it numeric. Because when you add in a string, it becomes like a character vector. So you can just make it as dot numeric, and then this 0.878 just becomes it goes from 0.878 to the regular form here. And you can just run these again, even with however many NAs you have. So that's just an overview of multiple testing corrections. So we can have NAs, it's just that you have to be careful because the NAs will be considered by many of these methods. So if you don't want them to be considered, then please don't have them. And thank you guys so much for watching. I'm Saniya. This is cute little Yangshi. If you found this helpful, please like, please subscribe as well, and please share. Please reach out with any and all questions. So just please subscribe for more updates, and please do check out my other content and other videos on multiple testing correction methods in more detail as well. I talk way more about this COVID example there as well, and differential expression gene analysis. But Yangshi, I think he stopped playing with fire, stopped with his little gambling and slot machines when he won this cute little doggy, because I think he's a little bit scared. Oh, are you scared of this guy? He wants to give you a hug. He won this guy and now he's just a little bit scared. He likes smaller things. I don't think the dogs and him are really buddies at the moment. He's kind of scared. But anyways, I hope that this helped you guys, and are there lots of methods? There are some additional tools on other hypothesis tests out there, which I can try to cover in another video as well. So please do stay tuned for that. There are other content available out there, like for instance by Roland Stevenson, family-wise error rates, controlling the FWER, strongly controlling. There's so much. So, but these are just very quick ones that I showed you, a few different methods. And Benjamin-Hochberg principle is used widely in a lot of applications, especially in bioinformatics. One thing we can do is see if we can find out which mystery adjustment method the DEC returned to us, because it gives us this adjusted p-value right here. And we can see which one it corresponds to. I can just take this and similarly just have a p.adj column, a vector, and I can add this to, I can just call p.adj, and we can see which one this is. This is just equal to p.adjusted. So let's see, I'm gonna add this to the end. Again, just looking at the 30. Okay, I'm just running that one, and I'm just adding this here, adding this column of adjusted p-values. And we can see which one does the DEC analysis returns. For the COVID severe and non-severe, it also has an adjusted p-value that I've been saying, okay, don't worry too much about that right now. But let's see what this actually is. So I can just say p-adjusted. I can just take this p-adj column here and then find this p-adj vector of values here. And we can see which of these it corresponds to. Okay. So we can see this p-adjusted value from the DEC. And which one does it seem like it matches? So if you know what I mean, the default p-value, we can already kind of guess what it is. The default returned by DECQ will be the Benjamin-Hochberg test correction. These line up. You know, you can see that it loves this. These are the same. The p-adjusted values that we get here are the same here. 3 times 2, 5, 8 times 10 to the negative 4. These are the same. In this 9.5211 times 10 to the negative 3 is the same here. These are all the same. These all are the same. So the adjusted p-value given by DEC will be the Benjamin-Hochberg adjusted p-values. So now you can see what they have done, and they must have run this test correction when they give you the p-values. So I just wanted you to understand that and see that here. So it's a BH method, it's the FDR method that they were using. So thank you guys and have a great day. And meanwhile, Yankee's gonna go and hang out with this little doggy. Aww. Thank you guys. I think he wants this guy, his little buddy. Aww. I'm Saniya Kuller, this cute little Yankee, cute little British. Hello, how are you? I'm really thankful that you watched the video. So please do remember to like, subscribe, and reach out with any and all questions. So thank you and have a wonderful day. Okay? Thank you. It's a little doggy. Woof, woof. Thank you, little Yankee. He's doing you a kiss. Aww. Thank you, guys. And don't do gambling.